So thank you all for coming to my defense. I'm going to be telling you about the work that I've been doing to scale microwave kinetic inductance detector readout. So in this talk, I'm going to start by telling you a little bit about detectors in general, and we'll talk about superconducting detectors. Then we'll get into the type of detectors that we work on in Ben's group, which are microwave kinetic inductance detectors. Then I'll tell you about my work scaling these detectors, and I'm going to take you through two main projects. The first is a new digital readout system, and the second is a new cryogenic readout cable. Then I'll conclude. So I wanted to start with a little story. When I was younger, like in high school, I used to be into amateur astronomy. And I mean like super amateur, like binocular level astronomy. And one of the coolest things I ever saw was the Ring Nebula. And if you look at it with binoculars, it looks kind of something like this. It actually looks a lot worse. I mean, this is like a 3-inch telescope and multiple stacked images, but I just remember thinking it was so cool. It was like this silver cotton ball. But now I'm going to show you what it looks like with the James Webb Space Telescope. So this is one of my favorite images released by JWST, and I just think it's amazing like how much more detail and color you can get in this James Webb Space Telescope image. And there are a lot of reasons why this image is so much more impressive than this one. I mean, for one thing, it's in outer space. But what I really want to focus on is the fact that we have these detectors that can sense light. And with these light-sensing detectors, we can build these really cool experiments and really learn a lot about our universe that way. So this presentation is going to be about light-sensing detectors, and specifically about a new type of light-sensing detector. But before we get into the pros and cons of that, I just want to give you a brief intro to detectors in general. So this is my little cartoon about how a basic detector works. We have some sort of photosensitive material that's in some sort of electronic circuit with some readout equipment that can measure the electric signals. And basically what happens is when light comes in, it changes the electronic structure of the detector, and that gets picked up by this electronic circuit and registered by the readout system. So in a typical, like in all the detectors that you're probably familiar with, the light sensing material is a semiconductor detector. And so the way at which it's actually reacting to light is through this band gap structure here. So semiconductors typically have this valence band, and when light comes in, it's going to excite electrons from the valence band up into the conduction band. And these detectors are really mature, they work really well, but it would be really nice if we could have something that was a little bit more sensitive than this like electron volt gap here. So there are some science cases for more sensitive detectors. So for example, biological microscopy, integrated photonics, and looking for planets around other stars are all cases where we could really benefit from like single photon counting detectors. So it turns out we can get the sensitivity with superconducting devices. Okay, but what is that? So I have a really basic explanation of superconductors, which is this. So some elements, which I've highlighted in like very light blue, when made really cold, and I mean like really cold, like close to absolute zero, become superconducting. So superconducting, you can think of it like a special phase of matter, like solid, liquid, gas. But there's some special properties here, and the one I want to focus on is when things go superconducting, the electrons form these little pairs called Cooper pairs, named after the person who discovered them. And these Cooper pairs are going to mediate the electronic structure of the superconductor, and more importantly, they're kind of bound together, and so that's going to provide this equivalent gap for us in a superconducting detector. So this picture isn't to scale, but the point is that the equivalent gap here in a superconductor where light's going to come in and kind of break apart these Cooper pairs is about 1,000 times smaller than what you can get with a semiconductor detector. So superconductors can be a lot more sensitive. And you kind of get like single photon counting with this situation. Even better, the amount of Cooper pairs that are broken is proportional to the energy of the photon. So if you carefully read out the electronic state here, then you can actually get the energy of the incident photon. And I'm not going to go into this in too much detail, but based on the way the readout works and the way these Cooper pairs recombine, you can read these out a lot faster. So you get like precise timing resolution. So hopefully I've convinced you that superconducting detectors have a lot of interesting properties and could be really useful for single photon counting, energy resolving science cameras. So you may be wondering, if superconducting detectors are so great, why don't we see them everywhere in all sorts of experiments? Now, truth be told, there are a lot of ways you could answer this, But the one I want to focus on is this idea that we need a lot of pixels. So Apple has the right idea here. The future is high resolution. We want to put as many of these detectors together as possible so that we can get more pixels and get better resolution science images. Now, unfortunately, creating large arrays of superconducting devices is really hard. And the reason kind of boils down to this cryogenic situation. So remember, I told you that the superconductors have to be kept really cold around absolute zero. So this is kind of a sample experimental setup for a superconducting detector. We have our detector down here near absolute zero. We have some sort of electronic readout system up here at room temperature, so that's 300 Kelvin. And then we have to have some wires that are going to connect these room temperature electronics to our cryogenic system. And there's no way around those just conducting heat into the fridge. So in this situation, with just one detector, we're happy. But as you add more detectors and more wires, I don't know if you can tell, the fridge is kind of yellow now. So it's kind of struggling to cool all the heat that's coming into the system. We're feeling so-so. If you have too many detectors and too much thermal conductivity going into your fridge, the cryogenic system will be overwhelmed. It won't be able to cool these devices. They won't be superconducting, and we'll be very sad. So one way around this is to put a lot of different detectors on one wire. And this ends up being a key concept for all sorts of superconducting detector arrays, because typically we want like thousands or even millions of these devices, and it's just not possible to engineer the wiring and fridge to handle that. So this multiplexing is a really important concept. A lot of the superconducting detectors out there aren't good at multiplexing, or it's not obvious how to multiplex them. But there is one that has inherent multiplexing built into the design, and that is these microwave kinetic inductance detectors. So this is what we focus on at UCSB, and I just want to tell you a little bit now about how they work, and I'm going to show you how they have this multiplexing superpower. What is an MKID? It's a superconducting resonant circuit made from inductors and capacitors. And this is a picture of a real MKID up here. It's basically just superconducting metal sprayed into the shape of a capacitor. That's this kind of big thing here. And then in the shape of an inductor, and that's the little thing on top. And that can be modeled by this circuit down here. So I feel like they look kind of similar, which I think is cool. And this thing is going to behave as a resonator, which means it's going to strongly absorb power at one specific frequency, and that's the resonant frequency of the resonator. So the name microwave kinetic inductance detector comes from the following. So the microwave comes from the fact that this is a resonator, and typically the resonant frequencies are in the microwave range, so we typically operate them between 4 and 8 gigahertz. Kinetic inductance, that's the way in which the device is photosensitive. So this inductor here is the photosensitive part of the circuit. When we actually detect photons, we use special optics to focus the light on the inductor. And so what happens is Cooper pairs break in that inductor. That changes the value of the inductance through the kinetic inductance effect. And that's how this device is photosensitive. Then the detector comes from the fact that we're just detecting single photons. OK, so how do we do that? So when we go to actually read out photons with an MKID, start with our circuit model over here, and we're going to send in a single tone that's at the resonant frequency of the resonator. And the signal we're actually looking at is going to be the phase of this readout tone. So when there's no photons, the phase is going to be pretty constant. But when photons come in and break Cooper pairs in this inductor, it's going to change the inductance, and that's going to end up shifting the resonant frequency of the circuit so that our readout tone is no longer on resonance. And what you'll see in the phase of the readout tone is that it will kind of track this resonator shift. So we'll get this pulse that goes up as the resonator goes over. And then as those Cooper pairs kind of recombine, the thing settles back down to equilibrium, and we get this kind of exponential decay here. And so this signal is really interesting because you can tell the time the photon hit the detector by the beginning of this rise, and the magnitude of the shift is actually proportional to the photon energy. So we can get the photon energy from the peak height of this pulse. OK, so this is just single photon readout. Let's talk now about the multiplexing. So here's our little MKID circuit with its frequency response. We can actually fabricate this in a different way. So we can change the value of the capacitor, and that allows us to change the frequency response of the circuit and move the resonant frequency over a little bit. So with these different responses no longer interfering, we can then connect them to the same wire. And what we're going to do is we're going to take these two probe tones and we're going to add them together. So now we have this superposition of the different probe tones, and each one of those is going to react only with its specific resonator. So we send this readout waveform, the purple thing, beyond our MKIDs, and then it may pick up some changes in the phase components of the individual signals from photon impacts. And then we use some really advanced custom electronics to kind of undo this addition operation and monitor all the frequencies in real time. Typically, we use something called an FPGA for this, which I'm going to talk about a little bit later. So essentially what the FPGA is doing is it's separating out the frequencies, it's going to convert them to phase, and then we'll look for photon pulses in each of the phases. And so we'll be able to digitize those signals and then reconstruct some sort of image. This is my dog, Cosmo, wearing a beret because he's a French bulldog. OK, so this is how the multiplexing MKIDs actually look in real life. So this is an array made where the superconductor is platinum silicide. It's on a sapphire wafer. This is kind of a zoom in here, so you can see there's 3 MKIDs I've highlighted. And then this is the microwave feed line, so this is going to feed in a superposition of all the readout probe tones to the MKIDs. And typically we multiplex about 2,000 of those per readout line. So in this kind of chip here, we've got 10 of these different readout lines, each multiplexing 2,000 signals, so this is a 20,000 pixel MKID array. So this is really exciting and cool that we're able to build these big arrays. But even with this multiplexing trick, there's some challenges that come along with actually building an instrument with this. So I want to show you those next, and then we'll lead into kind of the contributions I've made. OK, so this is the MKID exoplanet camera. Scary, real-life cryogenics, but just remember our picture over here. It's essentially the same thing. Down here at the bottom, that's where we have our MKID device. You can't see it because it's behind this magnetic shield, but it's down near absolute zero. Light's going to come in through this hole from the telescope and hit the array, and that's how we're actually going to do our observing. This instrument is currently stationed at the summit of Mauna Kea, where we're using it to try to look for planets around other stars. So light comes in from space and then excites the MKIDs. So this cable that you can see here, this is the main readout cable that's going to provide signals to and from the MKIDs. And sort of tying everything together now, so because we can only afford so many of these lines here connecting the hot stage to the cold stage, we really need to multiplex as many detectors as possible on each of these lines in order to build big arrays. So imagine here we have all of our different MKID resonators, frequency division multiplexed. And then to actually read this out, we need some really beefy electronics to try to separate out all those frequencies in real time. So this is the electronics rack that works with this experiment. It's got 40 FPGAs, it's 3,000 pounds, and consumes 3,000 watts, which is considered pretty weight and volume intensive by modern standards. So these are the 2 things that I focused on for my PhD. I redesigned this cryogenic readout cable, making something that was lower heat load and higher performance. And then I also redid the digital electronics with the goal of reducing the weight, volume, and power of the electronics. So first we're going to talk about the digital electronics, which is kind of probably what I spent most of my time on. OK, so I mentioned this thing called an FPGA a few times. So let's talk about what it is and what it's good at. So for my non-technical audience, I want you to think of the CPU like what's in your computer as a skilled worker. They can do a lot of different things, but at the fundamental level, they're really just doing one thing at a time, and they're kind of expensive. FPGA is more like a factory floor. It's this really kind of special, highly parallelized system. You can get a lot of things in and out. But you have to have this kind of specialized layout. You have to be careful about where you put your machines. You need to control the rates of the conveyor belts. You can't have conveyor belt 1 making boxes faster than conveyor belt 2 can pick them up. But once you kind of get all that layout working, then it can be a really cost-effective way to do a lot of processing. OK, so what is it really? So FPGA stands for Field Programmable Gate Array. And what it is it's this reprogrammable circuit that's got these kind of different components here. So FPGAs are kind of best known for having a lot of I/O capability. So that's all these kind of blue things over here. There are lots of ways and parallel lanes that you can get data in and out of these chips. It's also got these logic blocks here, so those can basically implement arbitrary gates and do whatever kind of math operations that you want. And then there are tools that come with the FPGA system that will program these switches and interconnects to then route all of your logic blocks together. So think of the logic blocks like the factory machines, and this kind of like routing switching, like the conveyor belts that go between them. So it can get pretty chaotic. That's kind of my goal showing you this picture here in the bottom right, is that there are a lot of wires, a lot going on, and generally speaking, you want to use as few resources on the FPGA as possible so that you give the tools like a lot of different options for how to find a solution to route between them. And if you don't do a good enough job with that, then the tools can just give up and say, we can't find a solution. Okay, so FPGAs are really cool, but they've kind of been around for a long time. And the new technology that I really worked with my PhD was actually something called an RF sock. So an RF sock is at its core still an FPGA. So that's what this programmable logic component is down here. But the RF sock also has integrated ADCs and DACs, which is like a really big advancement. And so the ADCs are what we use to convert the analog MKID signals to digital, go into the FPGA. The DACs do the opposite, digital to analog, they go to the MKIDs. And then if that wasn't cool enough, we also have a hardened processing system here that can run Linux, Python. It's got a gigabit Ethernet that you can basically just plug into the broadband network and log into this thing and then control everything. So it's really cool, and this whole like integration here provides a major reduction in the weight, volume, power, and cost of the system. So what I'm showing you here, this is the old Gen 2 electronic system. And this is the new Gen 3 electronic system that I worked on. This is the RF sock board here. And as you can see, it's just a lot smaller. It's a factor of 5 less weight and power, a factor of 10 less volume and cost, and it processes twice as many pixels as this whole thing over here. So it's really a huge kind of step forward for us. But unfortunately, it doesn't come pre-programmed. So this is actually the RF sock chip here. Here are the FPGAs that are on Gen 2. We couldn't reuse too much of the code from Gen 2 because for one thing, it's like a totally different architecture, separate ADCs and DACs, 2 FPGAs. It was also like implemented with tools that have been deprecated. And then if that wasn't bad enough, the grad student who worked on this project, after he graduated, became like a Christian monk. So totally unreachable. So for those reasons, we decided to kind of start from scratch with Gen 3. Before I move on, too, I want to mention this thing here. This is the IF board. I'm not really going to talk about it, but it's needed to do one more frequency conversion between the MKIDs and the FPGA. It's the same in Gen 2 and Gen 3, essentially. So you see that, that's what that is. OK, so I'm going to take you through the actual digital signal processing that we have to implement on the FPGA in order to do our MKID readout. OK, so here's our RF sock here. At a high level, we start with the DAC that plays out our superposition of readout tones, goes through the IF board and the MKIDs, comes back, and then we have to do that process where we separate out the channels. So it's kind of going to be something like a Fourier transform, but we do it in 2 stages. First stage is an oversampled polyphase filter bank. That's really a fancy Fourier transform that produces these like coarse channels here. Some of them might have 2 MKIDs, some of them might have 0 MKIDs. Then this direct digital down converter does a complex multiply at each signal to like fully center it in the bin. There's a low pass filter, and then we get our fine channels here. So after that, we're able to convert to phase, and then we do this special filter to filter our phase time stream, and then we get these photon pulses that can be triggered on. So I want to take a second to talk about the OPFB. I'm not going to go into a lot of detail about the algorithm, but I do have backup slides if anyone's interested. Funny story about the OPFB. It's like used a lot in like defense or like electronic warfare. So it was really hard to find an open source version of it. And at first I tried to see if we could pay someone to develop it for us. And unfortunately it was a defense contractor and they wanted like $10,000 per instantiation. So I kind of like got this chip on my shoulder and was like, I'm going to make an open source version. So that's what I did after a lot of effort. This is the Git repo here, and I just wanted to brag that this is the most popular Git repo in the Mazine Lab organization. It's not very specific to MKID Readout. It's really like a general purpose tool. But a lot of different people have like benefited from this work, I think in particular, because it's one of the first like open source versions of the algorithm. So I was really excited about that. Okay, so going back to our little simplistic block design here, I'm going to show you now a slightly more complicated version that is kind of more realistic to what is on the FPGA. So this is it down here. Don't be intimidated. I'm just showing you now like the data widths and like a little bit more detail about the different subsystems. So again, these blocks, these are the machines on the factory floor. Arrows are conveyor belts. So the processing, the original like separating out of tones is happening with these first 3 blocks. Arctan is how we convert to phase. This is the filter that we use to kind of reduce noise in the phase time stream, and then we're going to trigger and package up our photons. So there's a lot going on here, and remember I told you that you want to use like as few resources on the FPGA as possible? Well, this is the actual like implemented design. And we did not use very few resources. We tried our best, but this is kind of a flex, but also kind of like a word of caution. So I remember I told you that the tools can sometimes give up and like not find a solution for implementing your FPGA design. The first time that happened was when we only had the light blue OPFB implemented on this chip. So this view, by the way, this is showing you like this is the whole FPGA. Everything that's lit up is like something that's being used. So the first time the tools failed was only light blue. And it was basically like a battle all the way up until like, I think the first time we found the full solution was like January 2024. So that was a big effort between me, Jeb, and Alid, and we were working a lot on this over Christmas, and it was really exciting when it finally worked, but also I just want to point out that this is really just kind of like a huge design, and it's sort of a big deal that we were even able to get it to work at all. So I'm happy about that. And to illustrate that further, I have this picture here showing like an early unoptimized version of the design. This blue thing down here, that's the actual FPGA fan. This is the main voltage controller that supplies current to the FPGA. And as you can see, it's over 100 degrees C. So this is not what you want. And shortly after this, the whole thing, like the thermal protection kicked in and it shut itself off. But it's just kind of another way of visualizing like how much of the processing power we're actually using to do this MKID readout.
So Jenny, this was a figure that I didn't really understand in your thesis. So how am I supposed to interpret these colors on the left?
Right.
Sort of like a heat map in terms of...
So the different colors are just different pieces of the FPGA. So each of these blocks here correspond to like the labels here.
So if it's black within that square, it means it's not being used, but if there's a color, it is being used.
Right, and the color tells you which like piece of signal processing is using that thing. So you can it's kind of interesting to look at this, like oftentimes the things are kind of clustered together because like in the oversampled polyphase filter bank, you know, it needs to go from one area in the block to the next area in that block. So that's kind of how the clustering works. There's also, we kind of like manually placed this yellow block here. That's why it's got this sharp edge to try to help it route better. These like CLB, LUTRAM, BRAM, URAM, DSP, that's kind of like for anyone who works with FPGAs, those are the actual like FPGA primitives that we use. And so, I don't know, for anyone who's interested, that is kind of like another way of looking at the utilization. Does that make sense?
Yeah, but what would an ideal...
Ideally, you'd want to use like 20% of the chip. So I told you like it first failed when we only had the light blue. That's probably where a normal like engineering firm would stop and get another FPGA. Yeah. But we're very cost effective in the Museum Lab, so. You guys have any more questions about this? Okay. I have my little cookie figure here to show that you could bake cookies on the FPGA, which is exciting. But again, we did fix this. This was like early on in the process, but shows how much kind of processing power we're using. Okay, so now I want to switch gears a little bit and show you some of the actual like MKID data that we take with this FPGA system now that we have our working implementation. And I want to also point out that when we get our MKID devices from the fabrication, we don't actually know what like the best readout frequencies are. So we don't know the location of these resonators, and so it's important that the FPGA system also be able to like find the resonators. So going back to our block design for a second, that's what this calibration capture system is down here. So we get to pull data out from various points in the signal processing pipeline, capture them, and then we can kind of do our MKID calibration and setup. Okay, so I don't want you to be scared by the math, but I just wanted to kind of motivate this IQ loop down here on the right. So I think we can kind of all agree that this makes sense as the transmission past a resonator. right here in the middle. That's where we're most strongly absorbing a frequency. And this equation here is telling you the frequency response. And so if you take the magnitude of this complex number, that's how you get this transmission plot here. If you take the phase, you get this phase response here. And then if you plot this for every frequency on the complex plane, you get this IQ loop. OK, so this is just one resonator. Now we're going to look at the whole MKID feed line. So this is real data taken with the FPGA, showing it sweeping across the feed line. Each of these different colors is a different kind of channel that we're separating out. And so you can see as we go by the MKID resonators in the complex plane, we're getting these loops here. So these loops are really what we're going to read out and use to characterize the MKID. OK, so this is simulated data. Another thing I did was write this Python package to simulate MKID physics. And so I just want to show you in a clean format what the photon signals look like. So this is our IQ loop. After we've sort of characterized the resonator, we got the IQ loop. We're then going to pick a single frequency, this one, over here by the resonant frequency. And when a photon hits the MKID, this is the trajectory that we're going to take through the complex plane. And remember, we're actually just going to compute the phase of the signal, because that's a little bit easier to process. And so the phase of this is what gives us the pulse shape here. So the yellow is a simulation of kind of a lower energy photon. We get a shorter phase pulse. The blue is a higher energy. We get a bigger phase pulse. Wait for it to do it one more time. OK, cool. OK, so this is actual MKID data now that I took with that FPGA system. Here's the transmission, the IQ loop, and then here is a photon. And in this figure 2, I'm also going to take you through how we do the triggering. So we have this threshold level that we set. So when the phase goes below that threshold, we trigger. Then we start counting for this value here called hold off that we set per every individual MKID. So we count for hold off samples, and then we're going to save the minimum of the hold off value as the energy of the photon. So now I'm showing you here a phase time stream from an MKID, and I'm shining different colored lasers on the MKID. So there's the blue high energy laser, has the deep peaks. Kind of a less energetic red laser is the yellow, and then an even lower energy is the IR. And this is one of the red photons if we zoom in. And so you can make a histogram of all these different peak heights, and you can see they kind of cluster together. So we've got the blue, the red, the IR, and this is showing our ability to resolve different energies on the MKID. So this was kind of an exciting proof that we have this working, and we're able to get some decent energy resolution with our devices and our FPGA readout. Yeah?
The purpose of doing that IQ sweep is to find the 0 point. Is that it? From which, if you go back here, and once you're monitoring for phase and a photon comes, it looks like it starts at some 0 point and deviates. Is that the reason you characterize the IQ loop?
Yeah, there's something that I glossed over here was that there's a very light coordinate transform, and we're going to translate the IQ loop and rotate it so that the starting phase value is something reasonable for the arctan function. Arctan will wrap.
That is why you do the IQ loop thing in the first place, is to find that point you want to translate to.
Yeah, we got to find the resonant frequency we're going to read out at. We got to find the center of the loop that we're going to translate to. We got to look at how it's rotated and undo that. So kind of 3 things. OK, there's a lot more I could say about the software, but for this presentation, I'll just say that we can run a Jupyter Notebook server on the processing system that's integrated with the FPGA. So it's kind of cool. This is an example notebook showing kind of just basic MKID readout. This is how we took a lot of the data in lab. And since then, we've characterized a lot of new devices. Maja took some timing jitter data that we couldn't do with anything else. So it's been exciting to have this be actually a useful lab tool. Kind of like the oversampled polyphase filter bank, the whole MKID Gen 3 is also an open source project. So that's something that hopefully people will continue to contribute to. There's still a lot of work to do on the algorithms to set up the MKID array. And I'm excited to see kind of where it goes. OK, so in summary, we have a dramatic reduction in the weight, volume, and power of our readout electronics. This will make it easier for us to scale up to hopefully megapixel arrays. It also is much more reasonable to try to put something like this in space, on a high-altitude balloon or something, which we hope to demonstrate one day. And sort of the modern tools that we've used for this system are more adaptable, and we're able to integrate new signal processing changes. And so it should be hopefully more future-proof than the previous system. OK, so we have our new digital electronics. Now I'm going to tell you a little bit about this cryogenic readout cable. We're doing on time here. Okay, cool. Okay, so this cable, remember previously we discussed that it's important that we have something that's low heat load. This is also going to bring like really small kind of quantum signals to and from our cryogenic device, so we need something that's low loss. And then when you stick these electric fields close to each other, they can interfere. That's called crosstalk. So we want something that's like the different traces are well isolated, or else our system will be kind of too noisy, and when we add more pixels, we won't be able to read them out independently. So those are kind of the three most important things. We'd also like something that's flexible, has a small form factor, and is kind of easy to make. This is relevant for more than just MKID readout. It's really for all superconducting detector arrays, so in quantum computing, and then really anything that needs high-density cryogenic RF wiring. Okay, so this is kind of the fundamental design that we came up with. We have this material here, niobium titanium, and we make it into a foil, and we're able to weld that around wires to make kind of a coax structure. And the cool thing about this is that it's fully superconducting below 9 Kelvin, so another superconductivity property is there's no electrical resistance, so it's very low loss. And it's about similar performance to what you can find commercially, but half the heat load, so this was a really important thing for our experiments. And commercial projects also have these annoying like twisty connectors. This one has these nice push-on connectors, so it's a lot easier to install. So here's how the actual welding process works. We basically have a piece of foil on the bottom. We have these wires threaded through in this kind of like guitar-like structure, and then we have foil on top. And then this is me very painstakingly welding each of these things here. So the way that works is this is a micro spot welder. So these are 2 electrodes, and essentially it applies a big voltage difference between these 2 copper pieces here. When you reach a certain pressure on the material, it sparks between them, and the current goes through the thing you're welding, and it creates this little weld here. This is showing some early problems with like alignment and crinkling. We did eventually solve that, but I just wanted to this is a good picture of kind of the spot welding process. Connectorization is super annoying because niobium titanium, while it's a really great material for its cryogenic properties, it's very difficult to work with, and it doesn't stick to conventional solder. So essentially what we had to do to get this to work was to take this tiny capillary tube that's made of stainless steel, which also is not good to solder, but at least it's possible. So we have to thread the stainless steel capillary tube on this. This is an all manual process. Put it on this trace here, and then solder it. So this is going to be the center conductor of our little coax here. These are going to be where the ground plane connects, and it's basically going to form this like coaxial ribbon cable. So this was the first finished product here. It was a lot of tears, not actually, but a lot of practice with the microspot welder to get this to work, because if even one of these welds contacts a wire, it's going to short the whole thing, and the cable like won't work. So it's a very high stakes assembly process, but with enough practice, I eventually got it to work. And we installed these in that MKID exoplanet system in 2019, and the performance got a lot better because this has much better isolation. And then after this, we had a slew of science papers from MEC. So
I have to ask how many cables you went through before you ended up with that first successful.
Well, I will say too, the niobium titanium foil is super expensive, and we basically don't have the ability to get more. So it's also like you don't want to waste the material. So I practiced a little bit on other materials, scrap material. So only maybe like 1 or 2 of like the good cables, but a lot of practice on scrap material. Okay, so after that paper was released, we got contacted by this quantum computing startup called Maybell, and they actually wanted to commercialize the technology for quantum computing. So this is their icebox concept from their website, which is showing these coaxial ribbon cables all throughout this cryogenic fridge system. So we were able to do this DARPA SBIR program with them. We got some funding. I went out to visit them a couple times, and we worked on some upgrades to the cable. So I knew that the end of the cable was kind of a problem, this connectorization, where the electric field has to transition from this like kind of 3D cylindrical coax, this kind of like 2D intermediate zone, and then back to a smaller 3D structure here. So I wanted to simulate that in a 3D E&M simulator and see if I could figure out how to make it better. Are you sad, Omer?
I am awestruck.
Oh, okay, good. So I was kind of trying to figure out if there are certain things I was doing in the manual connectorization process that had a big impact on the performance. And one thing I realized was it was really important that this kind of cable here was connected very close to the connectors here. So this is a good construction and this is a bad construction. But unfortunately, this 0.6 millimeters here is just like totally impossible to do by hand, especially because you have to align 10 things of these next to each other. So that just wasn't going to be feasible to do by hand. But Ben actually came up with this good idea that you could build that little gap into the transition board here. So kind of what we're doing here is we're building in some capacitance right here between the signal and ground, and that's going to counteract the inductance of this wire here. So it's going to be a better impedance match. And so this is a picture of the board design here showing this tiny little gap. This is another handmade cable by me because I couldn't convince Maybell to test it for me. So I made the cable again, soldered it by hand. This is us testing it. And it worked a lot better than the previous system. So here I'm showing you the transmission of the cable from our 4 to 8 gigahertz range. We don't want much loss in this cable. So we want the transmission dip here, we're showing loss here. We want this to be as close to 0 as possible. So the previous cable is shown in this light kind of dotted line here, had a lot of ripples and reflections from impedance mismatches at the end. The new version, which is better matched, is this dark stuff here, so we're getting better transmission. So this was actually deployed at our MagIOX commissioning run in Chile. Ben, Jeb, and Noah went and did this. Cute picture of the chinchilla-like things that are at Magellan. And I think this was kind of a cursed project. I mean, I know Ben's smiling, but essentially the project never worked. And then they shipped it to Chile, installed these cables, and it worked for the first time, like when they were observing. Do you think that's fair? Yeah, I don't want to take too much credit, but it's kind of cool that it ended up working for the first time on the mountain. Typically, that doesn't happen. And then this was the tarantula in Ben's room. Okay, so since then, Maybell has continued to develop these cables. These are some pictures from their website. They've developed this like laser welding process. So instead of the super annoying spot welds, they use a laser to make these continuous welds here. This is a picture that I took for my Instagram story, so that's why it's got all the sparkles. It's like an Instagram filter. But this is the Vendor Expo Hall in March meeting in 2023 in Las Vegas. So it was really cool to see like something that I helped build be like actually on like the vendor floor. So that was really exciting. Okay, so we have successfully. No, we just get cables for free. I made this joke in Astro Lunch, but each cable's worth like a grad student salary, so. Maybell's probably going to make a lot of money, but we won't have to pay for them.
Oh, I see. So they're making a deal. Okay.
It's in the contract. But to be honest, the fabrication is still really challenging. So it's still, I would say, a high-risk technology, but Maybell's working on it. Hopefully, they can get something to work. Okay, so those are kind of the two projects I wanted to talk about. So now let's go through a super quick conclusion. I have sort of 3 main takeaways for you. First is that MKIDs are a powerful up-and-coming detector technology for energy resolving single photon counting cameras. Scaling these detectors into large arrays is challenging, but we can do it with kind of these modern engineering approaches. And this new RF sock-based digital readout and cryogenic cable will pave the way towards megapixel arrays, enabling new science and positioning MKIDs as a technology target for future space missions, or so I hope. Okay, now before I end, I just want to go through some quick acknowledgements. First, I want to say thank you to the Mazine Lab. You guys are awesome, past, present, future. Also to my committee, thank you for advising me, especially Ben and Jeb. Thank you to all my amazing friends. I had some people come and visit me while I was here, so that was really fun. Thank you to my family. I'm just going to flash through these. Especially Alex and Cosmo, my Santa Barbara support system. All the dogs in general. There's Maria and Lucia, they made it in here. And then to my dragon fruit plant. It's a long story I could talk about later, but I got this dragon fruit essentially right when I moved to Santa Barbara as a first-year grad student. And we've been on this journey together to try to get it to fruit, which it did like 2 years ago, but it's not self-fertile, so I have to get pollen from someone else. It's the whole thing. Didn't fruit last year, so that's why it keeps me humble. But it's exciting. Okay, so that's all I have for you.
So I guess at the very start you showed like a photon interacting with the inductor and the detector. Does a photon have to hit the inductor, or you have like a microwave like antenna somewhere? Like how do you actually couple the photons to the inductor?
So I'll spare us going back through like a million slides, but there's basically an array of lenses that goes over the array of MKIDs, and it focuses the light to hit the inductor. And then the inductor, we spend a lot of time engineering to have like special properties like uniform current and try to make it so that no matter where the photon hits, the response will be like reproducible. That's how we get like the energy resolution. We do have like stray events where it'll hit the capacitor or hit the substrate or something, but those just aren't very like high fidelity signals.
What is your realistic expected lifetime of Gen 3? Like, do you think the next grad student is doing Gen 4? Do you think 2 grad students from now?
Interesting question. So we are really like riding the wave of like the comms industry. So the comms industry, defense industry, like automotive cars, that's the reason why these companies are making boards like the RF SOC. And we really need super fast ADCs and DACs because we're dealing with like 4 gigahertz of bandwidth. So depending on if they're able to make an even better RF SOC with even bigger ADCs and DACs, we might want to migrate a platform to like a Gen 4. But I think, I don't know, hopefully like at least another grad student worth. Gen 2 was like 4 grad students, I think.
About 10 years,
Yeah, so let's say 10 years.
Kind of a personal question. Your defense is extraordinary because of all the skills involved here. There's open source programming, welding, simulations, like industrial development, and I guess I'm just wondering what you enjoyed most out of all those very, very different.
That's a good question. I'd like to do a lot of like different stuff. I think probably my favorite thing was like the most annoying parts of the FPGA design. So like looking at those really like crazy traces and stuff is something that I find personally exciting, but it's also something that most people hate doing, so that's why I feel like I gotta build that passion.